Crystals have been a major contributor to the electronic revolution that has taken place for the last 100 years. This is especially dominant in the area of wireless communications that, without crystal-controlled transmission, radio and TV would not be possible in their present form. As of a few years ago, the iPhone had 5 crystal oscillators to support processor clocking, real-time clocking, location services, video recording, and of course, cellular communication. As engineers, when oscillators are needed, we usually buy them already made. Few engineers design quartz crystal oscillators from scratch and know very little about the complex properties of quartz. We are not going to talk about oscillator design here, but hopefully we will understand a little more about quartz crystals.
These geometric shapes are made by a hunter that uses technology to catch its prey, a spider. It's taking great care to select the correct tools for the job and to arrange them in a precise way. Rejected material is flicked away. The spider arranges grains of quartz around the rim of its burrow. They must be quartz because quartz crystals have a very special quality. In the desert, a fine silk web would be scoured away by wind-blown sand, but the spider has a unique alternative. Within the burrow, incredibly fine silk threads are attached to the pebbles. The spider rests its leg on the strands of silk. The trap is set. An ant wandering in a minefield, unaware of the danger it's in. Inside each circle is a corolla spider, waiting. If the ant touches the wrong stone, its presence is betrayed by the merest brush of an antenna on the pebble. Quartz crystals have the remarkable quality of amplifying the tiniest vibrations with no distortion. They resonate along the silk to the spider and tell it exactly where to strike.
What is quartz? Quartz is a compound mineral comprised of silicon and oxygen, or silicon dioxide. Turns out, silicon and oxygen are 2 of the most abundant elements on Earth. Quartz is all around us in large quantities. About 10% to 14% of the Earth's crust is silicon dioxide and is easily seen. However, it is not suitable for making crystals for electronics in that form. In 1880, the brothers Jacques and Pierre Curie discovered the direct piezoelectric effect on quartz. They were able to measure a charge on the surface of natural quartz whose magnitude was proportional to the pressure applied on it. In 1881, the French physicist Gabriel Lippmann predicted the converse piezoelectric effect using the principle of conservation of electricity. In this case, a crystal is strained when a voltage is applied to it. Later that same year, it was verified by the Curie brothers. In 1921, Walter Guyton Cady developed the first quartz crystal oscillator. He also defined piezoelectricity as the electric polarization produced by mechanical strain in crystals belonging to certain classes, the polarization being proportional to the strain and changing direction with it. Quartz is anisotropic. Its properties, such as mechanical, electrical, and optical, are dependent upon the direction in the quartz bar. This leads to the quartz being direction sensitive, or one-wayness, as stated by Walter Cady. Because of this direction dependency, it will matter which specific angle of cut is used to saw the bar to make the individual crystal blanks. Every time the angle of cut is changed, it gives rise to a different electrical characteristic. A standard has been defined for axis designation of quartz bars. Y is the mechanical axis, Z is the optical axis, and X, looking in and out of the screen, is the electrical axis. The major cap faces are called the R faces, and the prism faces are called the M faces. There are several anisotropic direction-dependent properties of quartz: coefficient of thermal expansion, dielectric constant, electrical conductivity, hardness, optical index of refraction, and the piezoelectric constant, just to name a few. Here I am holding a naturally grown quartz bar from Madagascar. It's polished and has well-defined faces. Most of these crystals have numerous defects and fissures. Today, all commercial quartz used for the manufacturing of crystals is made synthetically. The natural supply of usable quartz was depleted many decades ago. No distinction is required between natural and cultured quartz. All modern-day crystals used in electronics are synthetically grown. Synthetic quartz is grown in steel autoclaves. Before growing a bar of quartz, a seedling of quartz is needed. The seeds are hung from wires inside autoclaves like sausages. Dissolved quartz then evaporates onto the seeds to grow atomic layer after layer to form the bar. The seeds are placed in the top chamber of the autoclave, which is about 5 degrees cooler than the bottom, to promote condensation of the dissolved nutrient onto the seeds. The seeds force the additional growth in the same crystalline structure as its own, hence a silicon dioxide bar is born. The quartz bars are grown in such shapes and sizes that labor cost and materials are minimized. The quartz bars take about 30 to 260 days to grow. In general, the slower the growth, the higher the quality. The typical temperature of the autoclave is 350 degrees C, with inside pressures around 2,000 atmospheres. The region around the seed crystal contains many defects and should not be used for the wafers. This is the typical internal construction of a crystal unit in an HC49/U hermetic holder, shown here with the case off. HC stands for holder crystal. This holder is designed to hold a round crystal quartz blank instead of rectangular. The blank is cemented to the internal post with a conductive epoxy at the flags of each of the electrodes. The leads are isolated from the metal base and cover with 2 glass seals. The cover is attached to the base in a special sealing chamber to evacuate the normal atmosphere. If one replaces the quartz dielectric with a non-piezoelectric one, this construction technique would simply produce a capacitor. A crystal will not pass direct current just like a normal capacitor. Here are some popular crystal case holders. The first is the surface mount type. The HC49/US is a smaller version. And pictured here is an HC49 like the example on the left with its cover on. The derivation of the equivalent circuit of a crystal is beyond the scope of this presentation. It requires the solution of a second-order differential equation describing the motion of the vibrating particles in the quartz crystal, including the effects of damping. The mechanical elasticity of the crystal is equivalent to a series motional capacitor. The vibrating mass of the crystal is equivalent to a series motional inductance. The mechanical losses of the crystal appear as an equivalent series resistance. C1, L1, and R1 form the motional arm of the crystal resonator. These are the same 3 electrical components in the previous figure. It's called motional simply because the crystal is a bulk acoustic wave device and physically vibrates when a changing voltage is applied. These motional components are valid over a narrow frequency range and will change with drive level, temperature, time, shock, and vibration, just to name a few. Also, due to the piezo effect, the motional arm values are only valid in the range of mechanical resonance. This is a critical fact when using the crystal equivalent electrical model for the simulation purposes. C0 is the shunt or static capacitance, which is primarily formed from the electrodes of the crystal plus the stray capacitance of the holder and its terminals. The shunt capacitance C0 is the only physical component in the electrical circuit and is present if the crystal is oscillating or not. This capacitor can actually be measured with a simple capacitance meter. However, the motional arm elements are equivalent and therefore are not real. The impedance of the two reactive elements of the motional arm, C1 and L1, is extremely high. The inductance value of L1 can be greater than 1 Henry, and the capacitance C1 can be less than 1 femtofarad, depending on the type of cut and the overtone involved. The enormous L1 to C1 ratio cannot be physically built with discrete components, and this is the major reason why quartz resonators are used instead. The motional resistance R1 can range from a few ohms to tens of thousands of ohms. Here is a schematic symbol for the crystal and its reference designator X. The pictorial represents a crystal blank with two metallized electrodes. The complex impedance equation is the parallel combination of the motional arm impedance and the static arm impedance. While the equation for the impedance exists, our interest is in the imaginary part of it. Here is the reactance curve that is plotted without going through the algebra of separation of the impedance equation. There are some frequency points of interest. The first is F sub s, and it's the frequency at which the motional capacitance C1 cancels the motional inductance L1. The frequency F sub s is called the series resonant frequency of the crystal resonator. This is the typical resonant frequency equation for the LC tank circuit. Ignoring C0, it's very important to note that the series resonance point, F sub s, is resistive and is equal to R1. Many oscillators are designed to operate at this frequency. The next frequency of interest is the anti-resonant or parallel resonant frequency F sub a. This is where the motional inductance L1 resonates with the parallel combination of C1 and C0. The series and anti-resonant frequencies are related by the following formula, since the parallel resonance includes the static capacitance. The region between F sub s and F sub a is called the area of usual parallel resonance. This entire region is inductive, and many oscillator topologies also operate in this region. We can separate most crystal oscillator circuits or topologies in two categories. A series resonant oscillator is a circuit topology that forces the crystal resonator to oscillate at the series resonance point of the crystal's reactive curve, which is the resistive point. A series resonant oscillator will contain no reactive components in its feedback loop. A parallel resonant oscillator is a circuit topology that forces the crystal resonator to oscillate in the area of parallel resonance on the crystal resonator's reactance curve, which is its inductive region. A parallel resonant oscillator will contain reactive components in its feedback loop. A crystal unit that is calibrated to its lowest frequency response is called a fundamental crystal or a fundamental mode crystal. The fundamental mode response is the most active and has the lowest resistance. A fundamental crystal can be calibrated at series resonance or in its inductive region. The next major response above the fundamental is called the third overtone. An overtone crystal is a crystal resonator that is calibrated to a frequency at a major response other than the fundamental. Above the third overtone are the fifth and the seventh and so forth. There are only odds and no evens. They are called overtones for a reason. They are not harmonics of the fundamental response. The major responses are not exact multiples of each other. Spurious modes can be a problem if the response is as strong as the main mode. When this happens, the oscillator may run on the spur instead of the main mode. This is called mode hopping. The crystal resonator equivalent circuit is now shown expanded to include the third and the fifth overtone motional arms. Because the shunt capacitance C0 is real, it stays in the circuit unchanged. This is why the overtone responses are not exactly harmonically related. The overtone arm's motional values are related to the fundamental arm by a relationship of n squared. The motional capacitance is divided by the overtone number squared. For the third overtone, C1 is divided by 9, and for the fifth overtone, C1 is divided by 25. The motional resistance is multiplied by the overtone number squared. For the third overtone, R1 is multiplied by 9, and the fifth overtone, R1 is multiplied by 25. The important outcome of the relationships between the fundamental motional arm compared to the overtone arms is that L1 is virtually unchanged. Many applications require the frequency of the crystal to be changed, in other words, pulled or deviated. This may be necessary to trim out the frequency tolerance, or as others call it, the set-on frequency. This is also necessary for making a voltage-controlled crystal oscillator, or VCXO. Adding a load capacitance in series with the crystal will move the frequency of the crystal from the point of series resonance toward the frequency of anti-resonance as its value is decreased. How far up the crystal curve with respect to F sub s will depend on the value of the load capacitor. Here's the equation for the change in frequency versus the load capacitance. The fractional frequency change relative to the series resonant frequency is the motional capacitance C1 over 2 times the sum of the load capacitance CL and the static capacitance C0 multiplied by 10 to the 6 power to give the result in parts per million. This chart shows the fractional frequency change in parts per million based on the varied load capacitance. This plot is based on a crystal motional capacitance of 10 femtofarads and a static capacitance of 10 picofarads. A delta F of 200 parts per million is achievable using a series load capacitance of 15 picofarads. Quartz crystal units are first categorized by how the blank is cut from the quartz bar. Recall that from earlier that quartz is anisotropic, and therefore depending on the various angles used to cut the blanks out, it will result in very different and important properties. The angle of cut is the primary determining factor for a crystal resonator's frequency versus temperature characteristics. Secondary factors are overtone, drive level, blank geometry, and electrode size and shapes. In 1929, it was discovered by groups in America, Germany, and Japan that the temperature coefficient of a Y-cut plate could be improved to become 0 at certain temperatures. The first 0 temperature coefficient cut discovered was named the AT cut. The true AT cut temperature response is made by cutting a quartz blank at an angle of plus 35¼ degrees rotated from the z-axis as shown. It was very important at the time of discovery because the finished oscillator could maintain good frequency stability above and below room temperature. The second 0 temperature coefficient cut was discovered and named the BT cut. Its angle is opposite of that to the AT cut at 49 degrees rotated from the z-axis as shown. The BT cut is about 50% thicker than the AT cut for any given frequency. This fact about the BT cut will become an important advantage at high frequencies, where the higher the frequency, the thinner the blank. Blanks can only be cut so thin, so higher frequency crystals are possible with the BT cut. However, the frequency versus temperature characteristic for the BT cuts are worse than the AT cuts, and that will be illustrated next. The T in the cut name stands for a temperature compensated cut, a cut oriented in a way that the temperature coefficients of the lattice are minimal. Here is a chart that shows the change in frequency with temperature for the AT cut crystal. Crystal's frequency change with temperature is a cubic polynomial function. The inflection temperature for the AT cut is 25 degrees C. You can see why it's a popular cut and why it's referred to as a zero temperature coefficient cut, because it only changes 10 parts per million over a wide range of 70 degrees C. Here is a family of curves for the increase in angle cut in 1 minute increments, with the last one at 16 minutes. These cut angles may be usable for ovenized applications at these higher temperatures. Here are the theoretical negative cut angles up to -5 minutes. I'm not sure if they have any practical application, but I decided to plot them anyway. Here is an overlay of the BT cut characteristic. While it's great for being a thicker cut, making higher frequency resonators possible, its 10 parts per million range is only about 30 degrees C. So far, we have only discussed the AT and BT cuts. There have been so much experimentation over the years with various cuts. There are 28 varieties of cuts currently documented in Wikipedia, as I have shown in this table. Here's a three-dimensional drawing I found of some of the various cuts. It doesn't show all 28 of the cuts in the chart, but it gives you an idea of the variety. Next up is one of the most important crystal cuts for airborne military applications. It's the stress-compensated cut, which is named SC. It was first theorized by Dr. Richard Holland in 1974 to overcome some of the shortcomings of the AT and the BT cuts like thermal shock. It has reduced frequency shift due to mechanical stresses and therefore is least sensitive to vibration. Unlike the AT and BT cuts, it's a double rotated cut. This diagram shows the orientation of the cut blank inside the crystal. Theta is the same angle as the AT cut at 35 degrees and 15 minutes relative to the z-axis. The cut angle phi is 21 degrees and 54 minutes relative to the x-axis. Here are the advantages of the SC cut. It offers a high turning point for higher operating temperature. Therefore, it offers higher frequency stability over a wide temperature range compared to other crystal types when ovenized. It offers improvement in aging performance, which is about 2 to 3 times better than the AT cut crystal type. It has a quicker warm-up time compared to the AT cut type. Therefore, it settles to its final frequency faster. Due to its higher Q performance, it offers better phase noise performance. It offers much less vibration sensitivity due to stress compensation features. The SC cut crystal is less frequency sensitive against change in spatial orientation relative to gravity compared to the AT crystal type. The SC cut has only a few disadvantages. Due to the high temperature operating point, it has a sharper roll-off at low temperatures, and therefore SC crystals are used only in ovenized applications and not in other configurations. So the extra power, weight, and volume is necessary for a heater and its control. It's harder to pull because of the high Q, but that's not a problem for fixed frequency designs. The manufacturing costs are high due to the increased labor cost. This is because of poor yields due to the double rotated cut, and for those reasons, the delivery lead time is higher compared to the AT cut. Here is a chart that shows the change in frequency with temperature for the SC cut crystal. The inflection temperature is 92.5 degrees C. This was chosen specifically to operate in an oven environment. Here's a family of curves for the increase in angle cut in 1-minute increments, with the last one at 4 minutes. It's easy to see how tightly controlled the frequency could be with the SC cut crystal in an ovenized environment. Here are the theoretical negative cut angles up to -2 minutes. Again, I'm not sure if they have any practical application. Usually, in a mechanical vibrating system, the thinner the substrate material is, the higher the vibrating frequency will be. This is the case for quartz blanks. The frequency constant N relates the thickness of the quartz substrate to the vibrating frequency. The values of N can be expressed in megahertz mils. For example, using the value of N for an AT cut crystal, the thickness of a 20 megahertz crystal would be 3.275 mils. This is only 3 times the thickness of the average human hair. Because of this, low-cost crystals are limited to about 30 megahertz for a fundamental AT cut unit. Now, if we make the same thickness in a BT cut angle, we could yield a 30.6 megahertz crystal, but it would suffer in temperature range performance. A fundamental 20 megahertz crystal at the 3.275 mils thickness could be made to operate in a fifth overtone to make a 100 megahertz crystal. The quartz crystal can vibrate in several different ways. Fortunately, the way the quartz crystal blank is cut from the original crystal can help determine the vibration mode. Here are some vibration modes and their associated cut designator. The CT, DT, and SL cuts have a face shear mode, which basically distorts the rectangular shape as shown by the arrows. The flexural mode happens on the J, H, and NT cuts. The longitudinal mode occurs in the E, the 5-degree X, and the MT cut. The tuning fork mode is a unique one and is used in a very popular application which we will cover in a minute or two. The AT, BT, and SC cut crystals are the most used, and they all vibrate in thickness shear mode. A few other cuts vibrate in this mode as well. Here is a crude animation I made showing the thickness shear mode in an extremely exaggerated form. Here's another animation showing what a third overtone vibrating crystal might look like. And finally, a fifth overtone. Here's another way to show the overtone responses. The bulk acoustic wave is 180 degrees on the opposite side of the blank. The same happens with the third and fifth overtones. I think this helps to explain why only odd overtones are physically possible. Tuning fork crystals, also known as wristwatch crystals, are one of the oldest crystal designs used for time control in watches, clocks, and nowadays in computers and other electronic equipment as real-time clock oscillators. These crystal units are being manufactured today in mass production in various package sizes and shapes. The most common frequency used for this purpose is 32.768 kHz. When the frequency is divided by 2 to the 15th power, it results in a 1 Hz signal. It has a temperature characteristic with the 25 degrees C inflection point and has a downward parabolic shape which is very close to the BT cut. Considering a wristwatch, making body contact for several hours a day, and the remainder at room temperature, this crystal provides a decent long-term reference. A crystal's frequency will change over time. In general, Crystals age logarithmically. They can age positive or negative, and in some cases, they can reverse that trend through time. Sources include lattice stress relaxation, metal diffusion, heat or excessive drive level, mechanical shock, absorption or desorption of contaminants. Crystals must be fabricated and hermetically sealed in an ultra-clean, ultra-high vacuum environment. It's typical during the initial manufacturing of a good quality oscillator to trim the initial frequency tolerance significantly tighter than the required tolerance for its operation. Let's say a system level requirement is 10 parts per million frequency accuracy. To ensure this over a 20-year product lifetime, the oscillator would need to be initially trimmed to, let's say, 2 parts per million to make sure aging over time does not exceed the 10 part per million requirement. Here's a common method used for the aging of plus or minus 10 parts per million spec over 20 years. Here's a common graph that shows the logarithmic aging based on stress relief and contamination and a combination of both. This shows how the aging trend can actually reverse itself. I called this a little about crystals for a reason. There is a ton of information out there since crystals are a key component in the electronics industry. One in-depth resource is the John Vig tutorial, which probably has the most information available in one place than any other resource I have seen. The Army has a good standard, MIL O 55310. One major topic not discussed here is vibration sensitivity and its profound effect on phase noise. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.